Right, for the last part of class, we are going to talk about, we're going to talk a little bit about more, we already talked about this, about deep learning, how it works, and particularly this idea of the transformer architecture. So in chapter 1, there was this discussion about the different branches of artificial intelligence. And the reason this is important is that sometimes people equate artificial intelligence with generative AI models or large language models or something like that. Kind of inaccurate, because artificial intelligence includes a lot more than that. That's super popular right now, and admittedly, it's where really all the development and action is taking place currently, and actually all the development and action. The stuff that's, we're accessing most of the growth and development here in large language models. But there's actually other types of models as well. There's the rule-based systems, which have been around for decades. There's still, applications for those. There are some other types of statistical models that we do. We are primarily focusing in this course down here on large language models, which is based on deep learning. So what I want to do with this transformer architecture is give a little bit more explanation about deep learning. Okay, how do they get their intelligence? So we had in 1958 the idea of the perceptron, and this is actually interesting, is that they came up with this idea of perceptron, kind of patterned after the human brain. And this was an article from 1958. I don't remember what the article source was. Expects to be able, so this guy, Frank Rosenblatt, he said he expects he'll be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Now that consciousness issue, I don't know if we've achieved. I hope we haven't achieved it yet, otherwise I'd be a little bit worried about that. But some people believe that we have achieved that, and I don't hopefully guess here yet.
Was that?
How do you assess consciousness? I think maybe independent action. So one of the issues of superintelligence, which again, we'll talk about that term later in the semester, is does the model have the ability to develop itself beyond the way it was originally developed? So as we look today, we'll talk about how we train models on a training corpus. Is the model able to train itself on things outside of its training corpus? And the consciousness idea is that it's self-aware, that it would actually understand. I mean, the reality is that the large language models can simulate being self-aware. If you ask ChatGPT, are you real? Say, yes, I'm real. I had an interesting Notebook LM podcast, which was a document that the people had studied, that they fed into Notebook LM, that actually was about the fact that Notebook LM was an artificial intelligence. And in the podcast, the two people are saying, wait, I'm not an artificial intelligence. What am I going to tell my wife and kids? They're not going to believe this, that I'm an artificial intelligence. And then the other person says, well, I think we are artificial intelligence. So they had this little debate among themselves, these two AI personas. They had a debate about whether or not they were real or not. So, I don't know what that means. All right, learn to differentiate between right and left after 50 attempts. That's been achieved. Perceptrons will make mistakes at first, but will grow wiser as it gains experience. We'll talk about that. So the idea of the perceptron was popular in the 50s, but then it was, again, AI winters, it was kind of abandoned for a while here. So we have a perceptron. Here's a picture of one. This is actually kind of a graphical depiction. So we have a bunch of numbers that come in that we multiply by some weight. So we add them together. We subtract out or add in a bias here, run it through an activation function that gives an output. Everything we did with Suno is based on this idea. It's founded in the idea that we have a bunch of numbers coming in that we weight, and then we add some bias to, and then the activation function, basically the activation function is kind of like a switch. It says, is it on or off? It's not really on or off because it can take different levels of onness or offness. That's kind of what the activation function does. Does that make sense? So this is kind of the foundational element. And if you take a bunch of these perceptrons and you put them into a network, you have a bunch of numbers going in and a bunch of weights here. And then basically each one of these dots here, all it's doing is adding the numbers up. Each number multiplied by a weight. And then it's putting in a little bias there. The bias is kind of like an offset thing. But it's putting that in, and then it's just feeding it through, layer by layer. So here's the input layer, here's a, what do we call these layers in the middle? Those are the hidden layers. What is the purpose of the hidden layers? What do they do? Is that a quiz question? It sounded vaguely familiar to me. So what do they do? Why do we have the hidden layers?
To account for certain things to give you more accurate results.
Yes, exactly. They account for certain things. What certain things do they account for?
Patterns.
Patterns, yes. Okay, excellent. So at the hidden layer, the best answer for that quiz question, hopefully somebody put this, pattern or feature detection or pattern detection. Same thing. So what happens is the network looks for some combination of inputs. High number, low number, high number, low number, whatever. Some combination of inputs. And then it tries to find that particular pattern. And if that pattern's met, it has a positive output. It says, yes, that pattern's been met. So on the input layer, it's looking for very, very general patterns. But in each of the layers, it's looking for more and more specific patterns. Does that make sense? So we're looking for kind of combinations of patterns, and those patterns represent something that's important. So as an example, we'll talk about later in the course, the vision models, models that are able to look at something and say, is this a chair? Is this an animal? Is this a vegetable? Whatever this is. And really how these vision models work is they look for patterns. They say, oh, if I see two circles, or first do I see some lines that go together in kind of a shape, that makes a circle. If I see two circles next to each other, below them I see a triangle, and below them I see an oval. Those are each patterns. And if you put those patterns together, all right, good luck, Pearson. Take your name card, please. I can't be responsible for losing that. Yes, go to another meeting. So if the pattern of two circles, a triangle, and an oval, what are we looking at? Two circles, that's a face. Do any of your phones do face detection like when you take pictures? That's how it works. Is there's layers of the network, and the hidden layers detect those patterns. They detect what a face is. And a face is kind of complicated, but the model learns how to do it. So we have input layers, hidden layers, and output layers. Okay, these are the weights of the models. The weights are simply what we multiply each of the inputs by in order to detect the patterns. High numbers, low numbers, what's important, what's not important. Okay, when we train the model, here we have the corpus. So what's the corpus?
That's
the big data set. Big data set. We're talking about not gigabytes, terabytes, or petabytes. Tons of information we feed into the model. We pre-process it. The model does not understand words. Okay, what are these dots here? What are these dots?
number.
Yeah, what goes into each dot? Yeah, it's just numbers. These dots are the perceptrons, and they only take numbers in. That's all they can take. Please, Gabe.
A dot would be a token.
No, the dots, these circles here, they are perceptrons. The last slide. So they're basically, you have a bunch of numbers coming in that you multiply by weights, and then add a bias, and then
Numbers coming in come from.
they come from the input. That's what we're going to get to. We're going to have to pre-process this.
Inputs aren't the tokens.
Well, I'll show you. You're asking exactly the right questions. Just a second, I'm going to get my little clicker here so they don't have to stand by the computer. Right. All right. So the prompt that we gave the model is words. Oh, it isn't. It are words. Is it our words? Our words. So they're words. Thank you. Anyway, the words come in, but the model doesn't take words in, it only takes numbers. So what we first do is turn each word into a token. You know, it's not even each word, it's each part of a word. Common words have a token assigned to them. Less common words, for example, Gabe. There's probably no token for Gabe. There's a token for maybe Gab, since that's a word, and a token for E. When we put those together, there's two tokens that represent Gabe. That makes sense? We can actually verify that in a few minutes when I show you the token, the tokenizer. So we take the words and turn them into numbers, and those numbers are simply used to look up the embeddings in the vector database, which we've already talked about today. Okay, so basically what we have, and I'll show you a visual representation of a vector, but basically we have Gab represents 1,000 numbers. E represents 1,000 numbers. You put those two lists of 1,000 numbers together, it represents you. Gabe. Or it represents Gabe in general, not necessarily you. So the embeddings are simply the semantic representation of the tokens. How do the embeddings know what they are? Train the embedding model. We're going to show how to do that in just a minute here. Does that make sense?
I have no idea really what numbers mean.
Oh man,
They're within.
we really don't. I'm going to give you an artificial example in a few minutes. It's just an artificial example. We really don't know what the numbers mean. Okay, more later on that. All right, then the output is a bunch of numbers, but of course, we don't want numbers. What do we want as an output from our large language model? The answer, right? So what it will do is it will take that output. Oh, actually, I'm sorry, we're at the training stage yet. We will take that output and we'll back propagate. So the input is the word. Give me a word from a poem. What's that? Wonderful. Give me a sentence from a poem then. Okay, what's the first one? What's tell me not in mournful numbers. Okay, so I feed in tell me not in mournful, and it has to come up with the answer. And it predicts that the next word is shoe. No, the next word is number. So what it does is it says, okay, I'm going to go back through the network, and everywhere it said shoe, I'm going to decrease the weights. Everywhere it said number, I'm going to increase the weights. So the next time, there's a better chance that if I say, tell me not of mournful, it will give me the answer numbers. Does that make sense? That's what backpropagation does. Backpropagation basically says, if we don't get the right answer, let's adjust the weights so that next time we have a better chance of getting the right answer. Okay, that's the training process. We use unsupervised learning. That basically means we just give it the inputs and let it figure out what's missing. Basically, you give it a bunch of words, they call it a bag of words, and you omit some words and have it try to predict what those words would be. It's unsupervised because you don't have to sit there and tell it what every word is. It will figure it out on its own. Okay. Self-supervised learning, give it some words, let it predict the missing words, then we backpropagate. So backpropagate, and I'm not going to go into the gory details of this, basically it's using mathematics to go into the network and adjust the weights so that next time has a better chance of predicting the word we want. And it says it's over and over and over and over again. It does cost truly millions, if not billions of dollars to train these models in terms of the amount of compute. I mean, it's unbelievable. Okay, we have to do alignment. After we train the model, they usually don't give good answers. Alignment is kind of like training, but it's different, and I'll explain why. So we have alignment data, and that is labeled data. What happens is, if you just train a model based on the internet, does the internet contain truth? Yes. Does it contain error? Yes. Does it contain things that are wholesome activities? Yes. Does it contain things that are violence? Yes. So what happens is the models do crazy things after we train them based on from the training corpus. So we have to align them around human values. The way we do that is labeled data, which we ask humans to tell, is this good or is this bad? Dave?
This would help with, I mean, I assume if the corpus that you gave it to train on was full of contradictions, it would just keep adjusting the weights back and forth because it just have one correct answer to set alongside.
Exactly. Yeah, because there actually isn't always one answer. If I said, tell me the beginning of that poem again, I should know this.
Tell me not in.
Tell me not, what's the next word? Of or in? In. Well, it could also be of, right? Tell me not of why you love me. Tell me not of where we're going. I mean, there's a lot of things that could be the answer to it.
Usages where.
There's a lot of usages, so the point of that is there's not always just one right answer. But there are certainly better right answers and worse right answers, and backpropagation leads us more towards better answers. Does that make sense?
We're defining better as accurate.
Better as more likely to happen in the real world, based on the corpus. So just simply in the corpus, if there's things that are repeated patterns, they're more likely to show up in the future. So we train on them. And in fact, when we train on a corpus, I don't know if I mentioned this in the reading, but it's not just one pass through the corpus. They have this thing called epics, where we actually take these 100 trillion words, feed them through the model and backpropagate on each of them, and then feed them through again, and feed them through again, and feed them through again. And even with the fastest computers in the world, it still takes weeks, if not months, to train these models. Does that make sense? All right, are we good? All right, a little more of the story. So when we're doing alignment, what we actually do, and next week I'm going to have you do an assignment relating to this alignment, is we have humans actually look at the outputs. In fact, you do this sometimes when you use a model and it says, here's two answers here, pick which one. Now, is one of them good and one of them evil? Usually not. Usually it's like one is better than the other. But what they're trying to do is use your human feedback to help align the model so in the future, it will give even better answers. Does that make sense? Okay, alignment is essential. They call this reinforcement learning from human feedback. It guides the behavior. It helps lead the model to get a better answer. Okay, very important. Reduces toxicity. We'll talk about that later, but toxicity is basically things like illegal or immoral kind of things that
It depends on the human's view.
that, alas, we'll talk about that issue. There's this issue called an echo chamber that comes up a lot, which is if you have bad values, the model will represent them. Yes. So it definitely depends on the humans and what they think. Prevents prompt injection. We'll talk about these things later in the course. So it basically makes it. This is called fine tuning. So alignment, we align the model through fine tuning. So I want you to understand that idea of fine tuning. It's different than the basic training. Training is just simply feed the corpus in, update the weights through backpropagation. Alignment or fine tuning is where we fine tune the model to do exactly what we want it to do, to answer questions, to help us with our analysis or whatever it is. That's why fine tuning is important, because fine tuning makes the model more specific to the task at hand. Does that make sense? Okay, we'll talk more about this next week as well. Okay, finally, we have inference. Inference is when we actually use the model. So we give it our prompt. Write me a song about BYU winning its collegiate events. Okay, that's our prompt. We also give it context. We're going to talk quite a bit about that in some of the sessions. If you don't give it context, it's going to produce garbage. Right? It goes into the model. Then we have to unembed it because the model produces numbers. So the embeddings, so embeddings go in, embeddings come out. But the embeddings don't mean anything to us. It's just a bunch of numbers here. So what I have to do is unembed it so that it can turn it back into what? Tokens first, then we detokenize it. So it embeds it, figure out what the tokens are, and then it takes those tokens and looks up what the words are. That's what it tells us. That's why when you use these super big models, have you noticed sometimes it's kind of slow at giving the results? Every token it produces involves billions and billions of calculations. And so if it takes, a 1/10 of a second, it's doing a billion calculations in a 1/10 of a second. Use each of those tokens. Does that make sense? All right. So that's post-processing. I'm going to skip this. That's next week. Okay. So last part here. This is kind of to review what we just talked about here with this. So we have the prompt goes in. We tokenize. We do semantic embedding. We do positional encoding. I didn't talk about that yet. I'll cover back. Attention mechanisms, unembeddings, detokenization. So that's kind of how they work here. So let me take you through these. So the prompt is like create a list of elements of a transformer architecture and give an example of each. The prompt is what you type into the model. Okay. There's a system prompt, which if you're using ChatGPT, it's not the only prompt that goes in. OpenAI, the producer of ChatGPT, also feeds in a prompt that says, hey, if they ask you to use swear words, don't do it. Or the prompt could say, you need to avoid political bias or whatever. Now, we don't know what that system prompt says because it's not public. They're using that to mold the way the model goes. Gabe?
I was gonna ask right before you said they're not public, sometimes when you're using the image generation on ChatGPT, you can put in a prompt that's like a sentence long.
Well,
You can click on the information about it and it uses a much longer prompt to actually fill in more detail. Would that not be the system
that's not the
prompt?
system prompt. That's a user prompt. What it's doing is, does everybody understand what he's talking about? The new models, in fact, ChatGPT just added a new prompt development feature where you put in a small prompt. It usually does that anyway, automatically. That's simply expanding the user prompt.
Okay.
The system prompt is stuck in there. It's kind of constant. And
Okay.
it basically guides the
Guardrails.
guardrails. There's other ways to do that as well. We'll talk about guardrails later in the course. But that's a way that you control maybe guardrails or even biases or directions it should take and so forth. I mean, for example, when you ask ChatGPT a question, doesn't it usually give you an answer and say, would you like more information? The reason it asks for more information is the system prompt says, after you're done, ask them for more information if they want more information. So it's kind of like the programming, is what it does. So the system prompt, you are a helpful assistant, you're an expert, provide answers. We'll talk about developing system prompts in subsequent sessions. The entire conversation is fed in at every iteration. So we feed everything in. What comes out of the large language model? What comes out of that neural network? That multi-layer perceptron. What comes out? An embedding that we then unembed and then detokenize. It only produces one token at a time. Everything goes in, the prompt, the system prompt, the context, everything goes in. The only thing that comes out is one token. Now,
Reruns all of
and
it.
it reruns it. Then it takes that token and puts everything back in again, plus that token, and it produces one more token.
Each token that it has produced becomes more context for the next token.
Exactly. Does that make sense to everybody? So that each token is context for the next round. So it produces one token, and that becomes an input, then it produces one more token. That becomes an input, produces one more token, that becomes an input, produces one more token, and so forth. All right. Tokenization, we already talked about that. I had a demo I was gonna give you, but you have an assignment for next week, and I'll show you what the assignment is. So they don't understand numbers. Here's the platform. So your homework assignment will be to go to this tool here, which is the tokenizer, and you will type in a sentence and look at the tokens. It's a contest to see who can come up with the 5-word sentence that has the most tokens. So here, if you look at this, Professor Sampson wasn't a professor at UVA. Professor is a token. Samp is a token. Son is a token. Wasn't is a token. Apostrophe T is a token. A is a token. Professor is a token. At U is a token. V A is a token. And period is a token. So your assignment, one of your 2 exercises, is going to be to do some tokenization using this little tool. And if you can come up with, and by the way, I shouldn't tell you this, but I had last semester, some student came up with a thing that had like 5-word sentence that had 50 tokens.
The high score.
That was a high. It was about 50, I think, was the record. Okay, does that make sense? Tokenization is basically split the words into a bunch of numbers that have embeddings. That's what we do next. Why do we do embeddings? Meaningless. So pizza, there's the number for pizza, exclamation mark, pregnancy, and a search. So here's a bunch of tokens here. They don't have anything to do with each other, so we have to vectorize this. So the vectorization I'm going to cover next week because we're going to talk about what's called resource augmented generation. And Michael, that's where I'll show my little demo of the little semantic map. Okay, so I'm going to skip that for now. I'm going to skip these things because that's actually next week's topic. Okay, so they embed one at a time. Back in work, we're talking about that. Positional encoding. This is key. So here I have 2 words. Explain why good tasting junk food is bad for your health. Explain why bad tasting junk food is good for your health. They're the same words, but in a different order. So what it does in positional encoding is said, how do the position influence the embedding? So it basically tweaks each of the embeddings based on where it is in the sentence. Is it the first word, the second word, third word, and so forth? Okay, I'll skip that for now. That's kind of the details. Okay, attention mechanism, we've already talked about that. Peter, I'm gonna have you take the last 5 minutes to do your intro. Is that okay?
Yeah, for sure.
Attention mechanism, we talked about that. What does the attention mechanism do?
It relates the words together to form.
Each other, yes. So that's the key. The magic of this is that it takes all these tokens or all these embeddings and it says, oh, this one's with this one. Puppy is with love, so therefore it's about Donny Osmond's song or whatever, you know? So it sees the patterns of the embeddings that go together. Attention mechanism, relationships between the words, words that modify the words. So here, the animal didn't cross the street because it was too tired. It is the animal in the street. The animal didn't cross the street because it was too wide. What does it mean there? Was the animal too wide? No, the street was too wide. So what does it mean? It depends on the context. In the first example, it was too tired. It was the animal that was tired. In the second example, it was too wide, so it was the street that was too wide. Because the model and the embeddings has learned that streets have width. And that animals can be tired. Does that make sense? Okay. So that's semantic embedding. So basically, you look for patterns in the data, feature detection. We already talked about that. What patterns relate to appropriate output patterns? And then we backpropagate. So here's an example of an embedding matrix. I'm not going to go through the math, but here I was trying to determine, in this case, it was the name of a Harry Potter character. So I'm not going to take you through the math, but it finds the most likely output for all of the, tens of thousands of tokens. It predicts the next word in the sequence. Okay, temperature I'll cover later. Okay, it puts the output on and starts over again. So it's what you said, Gabe. So what it does, it produces one token, it adds that to the input, produces one more token, adds that to the input, produces another token until it gets to what they call a stopping condition. Then it stops and says, oh, there's your answer. This is over and over again. All right, who is Elvis? So here, if you ask who is Elvis, it will say Elvis. Who is Elvis? Elvis, then it says Elvis was. Who is Elvis? Elvis was see how it's doing it like one word at a time here? Who is Elvis? Elvis was a singer. Who is Elvis? He was a singer in. This is called autoregression. Basically, autoregression means that it is recursive. It does it over and over again. It builds on itself. It just keeps repeating this pattern until it produces whatever the output is. Is this a miracle that this thing even works? It really is. All right. Stochastic parrot. It regurgitates what it knows. They call it a stochastic parrot. All it does is just looks up tokens. It tries to figure out what's the next token. What's the next token? Most likely token. A lot of this stuff we're going to cover next week. Next session next builds on that. I'm not going to take you through that. Okay, that's it. Our topic next week is that LLMs are part of bigger systems. So, all right, I know this is very hard to believe, but all the cool things we saw with Suno and with the notebook LM and stuff like that, all build on perceptrons. There's other things to them as well that we'll cover in later class sessions. But this idea of having inputs, looking for patterns, trying to see if we can replicate these patterns, train this, that's kind of how it works. That's our discussion of under the hood. This is the most under the hood we're going to get this semester. After today's session, we mostly talk about, well, what do we do with these things? How do we piece them together so they can accomplish